Hello and welcome. In this video, we will introduce Henry Darcy, define Darcy's law, describe a Darcy tube, and then demonstrate the Darcy tube's use. Henri Darcy, anglicized to Henry Darcy, was a French engineer famous for his work in the city of Dijon, southeast of Paris. In Dijon, Darcy was responsible for modernizing and improving the city's water system by installing a 12.7-kilometer long aqueduct that fed 120 street fountains via an arterial network of iron and lead pipework. In 1840, Darcy became the chief engineer for the Department of Côte d'Or, a regional governmental district that contains the city of Dijon, and would in 1848 be named chief director of municipal service in Paris. Unfortunately, failing health would force him out of public service in 1855 at the age of 52. In 1856, 2 years before his death, he published The Public Fountains of the City of Dijon, a treatise on the design and construction of the city's municipal water system. The work also contained his experiments on sand filtration that defined the relationship of fluid flow through porous media, which would later come to be known as Darcy's law. Darcy's law describes the flow of a fluid through a porous medium as a linear relationship. The flow rate, or discharge of a fluid Q, is the product of the following: the cross-sectional area of the pipe or aquifer, A, the hydraulic gradient, which is the change in hydraulic head height, delta H, over the flow distance, L, and the hydraulic conductivity of the media, K, which defines its ability to transmit the fluid. In order to determine these properties and their relationship, Darcy created an experimental apparatus which today carries his name, the Darcy tube. Darcy's sand column apparatus, as seen here, was constructed from a 3.5-meter steel tube partially filled with sand from a local river. Water flowed into the top of the cylinder, fed by a line connected to the municipal water system that Darcy himself had designed. For accurate measurements, Darcy's tube requires a steady flow state, and the reliance on the municipal water system was a source of problems for Darcy, as anyone else opening or closing a tap on the line would cause oscillations in the water pressure. It is said that Darcy performed these experiments late at night to minimize this issue. As water flowed through the column, hydraulic head pressure was measured by 2 mercury-filled manometers. The first, here, level with the input point, and the second, here, level with the output. Water was discharged into a reservoir at the bottom of the device, allowing for the measurement of the amount of water flowing through the system. Darcy's design, while limited by his level of technology, remains the foundation for our modern Darcy tube. Over time, with changes in technology, we've solved most of the issues that Darcy observed with his device, but much remains the same. Now, having given a brief description of Darcy's original apparatus, we'll cover the functioning and use of a modern Darcy tube. Water is fed into the Darcy tube via a constant head tank to overcome Darcy's problem of variation in inlet pressure. This tank provides a consistent source of water at a steady pressure head and without introducing air bubbles into the system. A tube from the water source, in this case a lab faucet, flows into the tank, while a bleed-off tube ensures that the tank does not overflow. It is important to ensure that there is a sufficient level of water in the tank at all times. Too low of a water level, like seen here, will allow air into the system and will not allow for steady state flow. Water then flows downward from the tank into the Darcy tube below. While Darcy's cylinder was constructed from steel tubing, our slightly more modern one is constructed of acrylic. The benefit of this is that we can see what's happening inside. For this demonstration, the porous material packed in the tube is comprised of small particles of terrazzo glass. The Darcy tube has 3 valves on its sides. This valve and tubing is the output for discharging water, which is being discharged into the lab sink as we prepare the apparatus. These outlets are connected to the 2 manometers from which we will measure the difference in hydraulic head pressure. While Darcy used U-shaped mercury-filled manometers, our manometers are simply filled with the water flowing through the system. While it is a simple system overall, it is crucial that you ensure that the water is flowing at a steady state and that your media is fully saturated before you begin any experimentation. Equipment ready and water flowing at a steady state, we can now use the Darcy tube to determine the hydraulic conductivity, the K variable in Darcy's law, by observing the discharge rate and hydraulic gradient. This will provide us with a quantifiable value of the material's ability to transmit water. Our first step will be to discharge water into a graduated cylinder over a set period of time. This will allow us to calculate the discharge rate as a volume over time. We will discharge water into this cylinder and record the length of time that it takes to add 100 milliliters. With the volume and time data in hand, we can now calculate and fill in the Q in Darcy's law. Q as a volume over time will be 100 milliliters over 16 seconds. However, Darcy's law's values are commonly converted to meters, so we will do the same. Thus, the Q becomes 6.25 times 10 to the negative 6 meters cubed per second. The second piece of data we need from the Darcy tube is the hydraulic gradient. To acquire this, we need two pieces of information: the distance between the two manometer outputs and the difference between the hydraulic heads. The distance between the two outputs is a simple matter of measuring, which, as you can see, is a distance of about 3 inches, or, more scientifically, 77 millimeters. The second piece of the hydraulic gradient is the difference in head pressure between the two manometers. This can be read off the manometers during steady state flow as you are discharging the water. Here we see that the upper manometer has a reading of 26.8 centimeters, while the lower shows a reading of 26.2, thus giving us a difference in head heights of 0.6 centimeters or 0.06 meters. With that, the required measurements for the hydraulic gradient are complete. As we return to the equation for hydraulic conductivity, we are ready to fill in our hydraulic gradient, I. The gradient is simply the difference in head heights, 0.06 meters, divided by the distance between manometer outputs, 0.077 meters. This gives us a resulting gradient value of 0.78. It is worth noting that we are dividing two values that have meters as units, thus the resulting value is unitless. The final piece of the puzzle is to determine the cross-sectional area of the Darcy tube. Luckily, this Darcy tube's diameter is the same as the distance between the manometer outputs, so we can simply use that measurement to calculate the area. After plugging in the distance between outputs into the formula for the area of a circle, we obtain a value for A of 4.66 times 10 to the negative 3 meters squared. With all of our data acquired and our variables filled, we are finally prepared to calculate our hydraulic conductivity. The result is a K value of 1.72 times 10 to the negative 2 meters per second. At this point, we should now ask, what does it mean? And how does it compare to the K values of other media? For that, let's look at a diagram of K values for common types of sediment and soil. In this chart from Freeze and Cherry, we can see the K values for a number of sediment types. Let's zoom in to make it easier to see. Here we have the approximate area of our K value, and we can see as we draw this line across the chart that our K value corresponds with a gravelly, unconsolidated material. Finally, if we bring back an image of the material in our Darcy tube, I believe we can understand why this material would be so good at conducting water. Its large angular grains and well-sorted nature point to a very porous media. Having determined the hydraulic conductivity of our material, we've completed our first experiment using the Darcy tube and Darcy's law. I hope that you found this introduction to Darcy and his work informative and useful.